Hello, everybody. Mr. Murphy here. What we're going to do today is we're going to talk about differential equations and their solutions. So let's start by just defining what a differential equation is, what I mean by that, and what solutions to differential equations look like. So here's what a differential equation is. A differential equation is an equation involving x, y, and one or more derivatives of y. So basically, it's an equation like this one that has variables and also has derivatives in it or rates of change like dy dx and things like that. So this is an example of a differential equation, basically an equation that involves a derivative. A differential equation can also look a little bit different. So sometimes you'll see it differential equations given as statements like in English sentences. So in that case, a differential equation looks like a statement involving one or more quantities. So those are variables. And their rates of change. So a statement about how quantities are related to rates of change, which is just another way to say differential equation. So this is an example of a differential equation. And with any kind of equation, it makes sense to ask, well, what does a solution look like? Well, let's take a brief pause and remember back to algebra. So if we had an equation like this in algebra, either 8th grade or 9th grade, we might be looking at this and you might have been asked, well, what's the solution to this equation? And there's certainly different methods that you can use to solve the equation. You can add 8 and then divide by 3. And when you do that, you get that x equals 7. So in this case, the solution to this equation was a single number. So the solution to normal algebraic equations are just single numbers. And we know that because we can plug 7 in to the original equation, and we get a statement that's true. The solutions to differential equations are functions. Rather than numbers, the solutions to differential equations are functions, like y equals this thing of x, or f of x equals sine of 2x or something like that. Is basically going to be a function itself that will solve the differential equation. There are two types of solutions to differential equations, as we'll see. The first type of solution is something called a general solution. So a general solution is a solution to a differential equation, which is a function that involves the unspecified value c. So a general solution still has c in the function, like plus c or times c or something like that. The second type of solution is a little more specific. We call it a particular or specific solution. So this is a solution to a differential equation, so again, a function, where the value of c has been specifically solved for from what we call initial conditions. Things like f of 2 equals 7. That would be an example of an initial condition. And we'll see examples of both of these. So we've got two types of solutions, a general solution and a particular solution. Generally, what happens when you solve differential equations is you start with a general, and then you get a specific solution from the general solution by solving for c. All right, so let's use this vocabulary and let's look at some examples of differential equations right now. So here's a couple examples. Feel free to pause the video and write these down in any of your example spots if you'd like. So this is our first differential equation up here. What we've got is 2x plus y prime equals 0. Pretty simple. I could restate it if I wanted to. 2x plus dy dx equals 0. So we see this is an equation with variables and derivatives in it. And what I'm asking us to do here, we're not going to solve these by hand yet. What I'm going to do is give you the solutions. And then what our goal is just to check and see that they work. Just like in the algebra equation up here, where we could check 7 by plugging it into our equation and seeing that we get something that's true. We can do the same thing here by taking this general solution and sort of plugging it into the differential equation here to get a statement that's true. So in order to verify this general solution, by the way, how do I know that this is a general solution? Well, that's because a general solution always involves the unspecified value c, and we see that right here. So how do we solve, or how do we verify that this is a solution to this differential equation right here? Well, we see that we have 2x plus y prime, and that's the derivative of y equals 0. So we have y right here. So what we're going to do is we're going to find the derivative of y prime, and we're going to plug it into our equation. So y prime would be negative 2x. The c gets destroyed, so it's just plus 0. So our y prime is just negative 2x. So what I'm going to do is I'm going to take my differential equation here, and I'm going to plug negative 2x, my derivative, into the derivative spot. And what we end up with is 2x plus negative 2x equals 0. And the goal is to see if this is true. And indeed it is. 2x plus negative 2x is 0, and 0 equals 0. So yeah, this is a solution. Verified. All right, good deal. Let's try this next one right here. We've got a slightly more complicated differential equation. Here we've got y double prime. So this is the second derivative. And then here we've got just the original function, y. So we've got a second derivative and the original function. There's no x's or anything. That's okay. So what we're going to do is we're going to take this general solution. We're going to verify it by plugging in what we need into this. So I guess what I'm going to need is y. I already have y. And I'm also going to need the second derivative. So let's start by taking the first derivative. Now you might have noticed that this y right here, ask yourself, is it a general solution or is it a specific solution? Well, it's got this c in it, so it's a general solution. The c isn't solved for. And this is a little bit different. The c is times function, so it's not going to get destroyed when we take the derivative like the other one. The derivative in this case will be c times, and then the derivative of e to the negative 4x. Well, the derivative of the negative 4x is negative 4, and then we have e to the negative 4x. So this is negative 4 c e to the negative 4x. That's my y prime. My y double prime would be the same sort of thing. So negative 4c times, and then we take the derivative of this again. So negative 4e to the negative 4x. We end up with 16c e to the negative 4x. Okay, so now we've got our second derivative. We've got our original function. Let's plug these into the differential equation, and let's see what we get. So when I plug in my second derivative in there, I get 16c e to the negative 4x in the y double prime spot, minus 16, and then I'm going to plug in my y. So my y was just c e to the negative 4x. And I want to check and make sure that this is 0. And indeed, 16c e to the negative 4x minus 16 times c e to the negative 4x. Those cancel out. And we just end up with 0 equals 0. So all right, this is verified again. So this function solves that differential equation. This function solves this differential equation. These are both solutions. So on the practice and on the formative, what you're going to have to do is, for one skill, check that an equation, that a function solves a differential equation by taking derivatives and plugging things into the differential equation. Okay. Now let's find what we call a specific solution. So in this example down here, what I want to do is verify the general solution, then find the particular solution of the differential equation through the point -3, 2. So we've got 2 steps to do here. Let's do this in 2 different colors. First, let's verify the general solution. So I've got this diffeq, this differential equation, and this general solution. So why don't you try it yourself? Feel free to pause the video if you'd like, and then try checking this general solution in this equation. Okay. So in my differential equation here, I see an x, I see a y prime, and I see a y. So I'm going to need to take the derivative of this. So my y prime will be, so it's c times x to the third. So the derivative will be c times 3x squared. The c doesn't get destroyed because it's being multiplied. So that's 3c x squared. So when I plug that into this, I've got x times 3c x squared minus, and then 3, and my y is the cx cubed that I started with. I'm going to check and make sure that this is 0. A lot of times things are equal to 0. And well, what we see here is we see x times x squared. So this is 3cx cubed minus 3cx cubed. Okay, all right. Yeah, that checks out. So 0 equals 0. So this verifies this general solution. This is a solution of our equation. Yep. Okay, now what we want to find is the specific solution, or a particular solution, through the point -3, 2. What that means we want to do is use the point -3, 2 to find the value of c in this. So we're going to take our 2, which is our y coordinate, and plug it in for the y in the general solution. And we're going to take our 3, which is the x coordinate, plug it in for the x. So we get that 2 equals c times -27. So c is equal to -2 divided by 27. I'm still not quite done yet. I've just found the value of c. So my specific solution, I need to take my general solution and rewrite it with this specific value of c plugged in for the c. There we go. That's our specific solution. It's not much different from the general solution. What we're doing is just taking a specific point and plugging it in to find what c has to be, what number it has to be to give me that. Okay, so those are the basics of differential equations. I know what you might be asking yourself. Oh, sorry, I got one more thing. So those are the basics of differential equations. What we're going to take a look at now very quickly here is just writing differential equations that correspond to this description. I mentioned this in the first little slide up there, is that differential equations can be like statements of things involving rates of change too. So let me show you how these work. It says the rate of change of y with respect to the variable x. This is a statement about a derivative. So what I'd say here is that dy dx, that's what the rate of change of y with respect to x means. It's the slope, the derivative, dy dx. It says it varies proportionally with the difference between x and 4. Well, the difference between x and 4 is a little chunk in parentheses that looks like this, x minus 4. And the phrase varies proportionally means that my dy dx is equal to some number k times x minus 4. So this is my differential equation from this statement. Dy dx equals k times x minus 4. Varies proportionally, we'll put a proportion or a constant in front of the x minus 4. Very related, down here, we've got another statement, the rate of change of y with respect to x. So that's dy dx. It says varies inversely proportional. So what this means is that my derivative is equal to k divided by, and then it says the square of x. So I'm going to put x squared down there. So this would be the differential equation that's described by that statement. Okay, well, now that we've got more of the basics of differential equations out of the way, I know what you're thinking. You might be thinking to yourself, man, this is cool and all, but I really want to be drawing awesome pictures instead of doing calculus. And to that, I would say, why can't we just do both? So this is one of my favorite parts, as you'll see. What we're about to do is we're about to draw pictures of differential equations so we can get more of a visual understanding of what's going on when we solve these differential equations. And that, my friends, is something called a slope field. So we're going to hit two things today. We just did the first thing, which is what are differential equations? How do we check solutions? What do solutions mean? And then the second part is slope fields. How do we draw differential equations and represent them in pictures? So a slope field is a graph consisting of short line segments representing the slopes of any solutions to the differential equation. And that's a mouthful, but what it essentially is saying is that we're going to take this differential equation, and because what it's basically saying is dy dx equals 2x, and dy dx are the slopes of y, we can plug in specific points and just draw slopes based on what the differential equation tells us the slope should be. So let me show you how this works. So I'm going to pick, I think, points along this vertical line first. I'm going to write out what we're doing, but very quickly you'll kind of get the hang of it and you'll start to do stuff in your head. So the first point I'm going to plug into my differential equation is 1, 0, this purple point right there. So according to my differential equation, dy dx would be 2 times 1, which equals 2. The x coordinate's 1. So this tells me that the slope at this point, is 2. So I'm going to draw a short line segment that has roughly a slope of 2. That's going to look something like that. A little curvy. Let's make it straighter. There we go. Just a short line segment that roughly has a slope of 2. Doesn't need to be exact. All right, let me go up a little bit. So let's try the point 1, 1. That's this point right there. So dy dx would be 2 times, and I only need the x coordinate, so 1. So it looks like that slope is 2 again. So I'm going to make the same sort of slope right there, roughly the same. And if I try the point 1, 2, same thing happens. Dy dx equals, we get 2 times 1, which is 2. So at this point, we have a slope of 2 again. And as you can probably guess, because this differential equation only depends on x, my slope at every single one of these points where the x coordinate is 1 will just be 2 all the time. So I can just go ahead and draw those slopes in there. This is a pretty nice differential equation. Okay, well, let's try another class of points. So I'm going to pick this point right there. Looks like that's 2, 0. So if I find the slope at that point, dy dx would be 2 times 2, which is 4. So that slope would be 4. So 4 is steeper than a slope of 2. So I want to draw my slope so that it's steeper than 2. So maybe a little something like that. Yeah, more or less that'll work. And because I know that every single point that has an x coordinate of 2 should also have a slope of 4, I can sort of repeat that in these other points. And then, yeah, we just repeat it for as many points as we can, or as many points are on the grid, and draw in a complete slope field. So why don't you try that? For the points where we have an x-coordinate of 0, and I guess it doesn't matter what y-coordinate is because we don't have any y's in the differential equation. And why don't you also try it for the points where the x-coordinate is -1? So what would the slopes be in those spots? And then try sketching those points. Okay, well, when the x-coordinate is 0, that would make a bunch of slopes where we would have 2 times 0, where the slope is 0. So I should draw in a bunch of slopes that are slope of 0 in these points. And points where it's -1, where the x-coordinate is -1, we have 2 times -1, which is -2. So I should draw in a slope that's roughly the same angle as these, just negative instead of positive. So maybe something like this. And as you can see, I'm not paying super special attention to getting the slopes exactly right. I just want things to be more or less accurate. And then the other slopes would be -4, so they would be even steeper. And we're starting to see here a picture of what the differential equation represents. So this picture sort of represents the general solution. In other words, the solution with just any plus c, because we could have a solution in here that moves up or down. And if I wanted to draw in a specific solution through, let's say we want to pick the point -1, 1. That would be this point right there. All I'd have to do is follow the slopes. So at -1, 1, I see them going up this way, and then these slopes are steeper, so things get steeper. Might look like that. And then if I go the other way, it looks like I'm going down here, but then these slopes go down to 0. And then things pick back up again, and then go back up like this. So this red parabola, this red curve, would be my specific solution through -1, 1. So the general solution is like all of the slopes altogether, and the specific solution is one curve that goes through one point. This is what slope fields can help us visualize. They help us visualize essentially what kind of curves will solve the differential equation. In this case, it looks like it's a bunch of parabolas that are just shifted up or down by c. All right, there's a lot of talking about one single slope field. Let's take a look at a couple more examples here, and then we'll be done. So sketch the slope field for dy dx, or y prime equals x plus y. Okay, so let's restrict this first of all. Let's make it a little bit easier to manage here, because this is going to be a little tougher. We're only going to do this section of the graph, I think. Yeah. So only out to x and y coordinates of 2, I think. So we've got y prime, or dy dx, equals x plus y. And what we're going to do here is we're going to pick points, plug things in, and just see what the slope is. Feel free to pause at any time and just try plugging in points and graphing the slopes on your own if you'd like. So I'm going to find dy dx at the point, let's do 1, 1 first, I think. So 1, 1 would be 1 plus 1, which is 2. So at 1, 1, I'm going to draw a slope of approximately 2. Next, I'm going to pick 1, 2. My dy dx would be 1 plus 2, which is 3. So this slope up here would be steeper. If I go down to, let's say, 1, 0, my dy dx would be 1 plus 0, which is 1. So that'd be a slope of 1. And then if I pick the point, let's say 1, -1, what would happen? Well, I'd have 1 plus -1, and that would make a slope of 0. So this point down here would have a slope of 0 right there. And you can keep on going and plug in more points in here and see what you would get. I'm going to go ahead and do that. And writing takes a little bit of time. So I think I might write one more here. I'll write 1 comma negative 2. So the slope for 1 comma negative 2 would be 1 plus negative 2, which is negative 1. Let me draw a slope of negative 1 right there. And then I would move to another line and do another bunch of points. So this point right here is 2 comma 0. 2 plus 0 is 2. So I draw a slope of 2. 2 comma 1 would be 2 plus 1, which is 3, slope of 3. 2 comma 2, slope of 4. So a little even steeper. And when they get steeper, they're kind of hard to accurately draw what those slopes are, but just try to get steeper. 2 comma negative 1, that would be 1. 2 comma negative 2, that'd be 2 plus negative 2, which is 0. We keep going. 0 comma 0, well, that would be 0. 0 comma 1, that'd be 1. 0 comma 2, that'd be 0 plus 2, which is 2. 0 comma negative 1, that'd be 0 plus negative 1. 0 plus negative 2 would be the next one. And you start to get a feel for the pattern of these as you're drawing your slope fields. So negative 1 comma 0, that would be a slope of negative 1. That. Negative 1 comma 1 would be negative 1 plus 1, so 0. Negative 1 plus 2, that would be positive 1. I'm going to go down now. Negative 1, that'd be negative 2. Negative 1, negative 2 would be even steeper downward. And then back here, negative 2, 0 would be a slope of negative 2 right away. Negative 2, negative 1 would be negative 3, and then negative 4 down there. Negative 2 plus 1 would be a slope of negative 1, and negative 2 plus 2 would be a slope of 0. So this would be our little slope field in this space right there. It is totally okay to write things out, especially if you feel like you don't want to make any mistakes. I think this is important because sometimes on the AP test in the FRQ, they'll have you draw slope fields only with like 6 points or so, and you want to make sure you don't make any mistakes there to get all of your points. So it's totally okay to write things out and see what the slopes would be by hand. But sometimes when you get comfortable with it, you can just do things in your head. What I want to do here, so in blue, let's sketch the specific solution through the point, let's say the point 1 comma negative 1. So what would that look like? Well, 1 comma negative 1 is right there. So we can see that our slope would start out being 0. Then if I move to the right a little bit, it looks like these slopes become positive, like they go up like that. So I should draw in something that looks kind of like that, following the slopes. If we go to the left a little bit, looks like we go negative, but then it kind of hits these slopes that are all negative 1. And I don't think it would really go past it. It would just sort of get closer to them. So we would go out to the left like that and then get closer to those slopes of negative 1. So there's our specific solution. That's what that curve would look like through the point 1 comma negative 1. Now, do I know what equation that actually has? No, I don't. But I can draw it and I can visualize what it looks like through the slope field. I think I'll do one more here. If you feel like you get it, totally fine. If you want to pause and go on to the practice, that's cool. If you'd like to do one more with me, that's fine too. So I think I will do this even smaller than before. Do that range right there. And for my differential equation, I'm going to do 1 plus y. It's my differential equation. So my first example depended on x. My second example depended on both x and y. And this example will depend on only y. So when I find my slopes here, let's start with the point 1 comma 0. So when I find my slope, 1 comma 0, that would be 1 plus y coordinate of 0 is 0. So that would be 1. So 1 comma 0, my slope is 1. at 1, comma 1, my slope is 1 plus 1, which would be 2. So I would go up like that. And then the next one, 1, comma 2, that would be 1 plus 2, which would make 3. If you'd like to pause and try the rest of these on your own, you can. If I go 1, negative 1, that's 1 plus negative 1, which would be 0. And then 1 plus negative 2 would be negative 1. Okay, let's move to the next one, 0, comma 0. So this dy dx would be 1 plus 0, which is 1, like that. If I go 0, comma 1, then my slope would be 1 plus 1, which is 2. And then 3 would be the next one. 0, comma negative 1. My slope there would be 1 plus negative 1. It's the y-coordinate, which is 0. Okay, so it's looking like I'm seeing a bit of a pattern here. The slopes look like they are the same across the y-coordinates, which should make sense because this differential equation only depends on y. So I can effectively draw in the rest of it from there if I don't want to plug anything else in. I know that at all the points where my y-coordinate is negative 1, I'm going to have a slope of 0. And at all the points where my y-coordinate is negative 2, I'm going to have a slope of negative 1. Likewise for 0, and a y-coordinate of 1, and a y-coordinate of 2. So then here would be this little slope field, and the solutions would kind of look like sweeping curves like that, or sweeping curves down almost, if we had to draw in specific solutions. Like if I wanted to draw in the specific solution at 1, comma 2, it might look something like that right there. So that's the specific or particular solution through the point 1, comma 2. We see that this curve has to like approach these 0 slopes right here and can't go past it, just because as it gets closer to these points with 0 slopes, it's going to end up getting a slope that's really close to 0. Okay, that's everything that I wanted to do with you guys today. That is checking the solutions of differential equations, all about differential equations and slope fields. Thanks. Have a great day. I'll see you guys later.